someone drop it? Was it a mistake?
Did you know that time's different when you move at different speeds? That when you move through space, you change the rate at which you move into the future? Well, you can't really notice these differences for everyday speeds, but for really high speeds, like for rockets traveling about half the speed of light, these time differences can be noticed. Let's take a look at the so-called twin paradox.
Well, bye. I don't know. I'll see you again.
Yeah, I guess maybe we'll see you. Sure, you know, well, it's all in the
dark out there.
science. Well, it is dark.
We brought a lunch, you know.
Now, while the traveling twin experiences weeks, the stay-at-home twin experiences years.
No, I think I'll just sit here and do nothing. Yeah, that sounds like, yeah, I'll do that. Oh, what is going on out there? Oh, my goodness,
I don't believe it.
I don't see you. I must relax. I can't relax. I'm too old to relax. Look at the size of this one.
Could a situation like this be true? You bet it can. This is time dilation. We can see time dilation by comparing clocks from different frames of reference, say from the Earth and from a high-speed rocket ship. Now, a clock can be anything that measures periodic intervals of time. To simplify, we're going to let the ticks of our clock be periodic flashes of light. Look at the light flashes emitted by the stationary rocket ship. Now, some time goes by before they reach the distant planet, but since there's no relative motion involved, successive flashes get to the planet at regularly spaced intervals. That's to say, both the sender and the receiver will agree on the time intervals between the flashes. Now, there's nothing unusual about this. But suppose the rocket ship moves. Look at the Doppler effect. An observer sees the flashes at shorter intervals. Suppose the ship moves fast enough so an observer sees the flashes at intervals twice as short as the ship sends them. Then if the ship moves away, just as fast now, an observer is going to see intervals twice as long. Like if the rocket sends a flash every 6 minutes, they'll be seen every 12 minutes by the observer when the rocket moves away, but every 3 minutes when the rocket's approaching. Now let's apply this to time dilation. If the ship passes by the Earth and moves away at the same high speed for 1 hour, and quickly turns around and then returns in 1 hour, rocket ship time, this 2-hour trip is seen by the Earth as taking place not in 2 hours, but in 2.5 hours. And this is because the ship and the Earth have been in completely different realms of time. Let's look at this in greater detail. Suppose that when the ship goes by the Earth, that clocks on Earth and on the ship are synchronized to 12 noon. Then as the rocket leaves the Earth, a flash of light is emitted by the ship every 6 minutes. That's 6 minutes rocket time. Then the ship emits 10 of these 6-minute flashes while going away from the Earth. The 10th flash is going to be emitted 60 minutes after leaving the Earth. Then the ship's clock is going to read 1 o'clock just when this 10th flash is emitted. Now suppose this is the moment that the ship turns around. Our Earth observers don't see the turnaround until they see the 10th flash. Now here it comes. It's going to take some time for it to get to them. Closer, closer, closer. Bam, there it is. 10 flashes, 12 minutes apart. That's 120 minutes, 2 hours. So that means it's 2 o'clock now on Earth. Now the 10 flashes the ship emits when approaching the Earth, they're going to be seen 3 minutes apart, or all 10 in 30 minutes. The first is 3 minutes after 2 o'clock, Earth time. The next is 3 minutes later, and so on, until the last flash is emitted just as the ship whizzes past the Earth. And that's going to be 2:30, Earth time. So a clock aboard the rocket ship reads 2 o'clock, while a clock on the Earth reads 2:30. This checks out. Check the figures. Now let's go through this once again. Watch carefully and compare the clocks. We'll get the same results if we switch frames of reference. The Earth will send flashes now at 6-minute intervals, and the rocket ship will observe them while again departing and returning on what for the ship is a 2-hour journey, 1 hour out and 1 hour back. While going away, the ship's going to see flashes 12 minutes apart. That means it's going to see a total of 5 flashes during this hour of going away. See that? Now while returning, the ship sees flashes 3 minutes apart. It's going to see a total of 20 during the hour of return. For the round trip, then, the Earth emits a total of 25 flashes. At 6-minute intervals, that's 150 minutes, or 2.5 hours. Same results as before. So from either frame of reference, a person on Earth ages more than a person in a high-speed rocket ship. It's not so much a question of who's moving and who isn't, but rather the different space-times experienced. The person on Earth remains in one space-time throughout the experiment, whereas the person in the rocket ship is in a completely different realm of time while traversing space going away from the Earth, and in still another realm of time while traversing space and coming back to the Earth. That's 2 space-times. 2 space-times separated by the acceleration of the ship and turning around. Now that acceleration is interesting in its own right. Get to that in general relativity. But we see that the details of that acceleration aren't really essential in this case. The principal significance of that acceleration is that it marks the changing from one space-time to another. Now, our twins have been in different space-times, and they can meet again at the same place in space, but only at the expense of time. Isn't that great? That's time dilation. Peace.
Where did the time go? Does anybody know? When did the day break? Did someone drop it? Was it a mistake? I've got a notion, circular motion, I'm flying out in the ocean.